Okay, so let's look at some conjugate pairs. So we're talking about conjugate acid-base pairs. So here is an equation here. We've got hydrogen carbonate reacting with water to make carbonate plus hydronium ions. Now, what we know is the hydrogen carbonate is a weak acid. And in this case, if we look at this equation, we can see that this weak acid here has a similar species on the other side, and that's the carbonate. It's the only difference between this acid and the base on the other side is that the acid on the left-hand side, the weak acid, has an extra hydrogen and an extra positive charge. That's an extra proton. And the reason it has that is that this weak acid, the hydrogen carbonate, the HCO3-, has donated its proton to the water. And in that, because it did that, it lost its proton and it became a carbonate ion. But because the water is accepting a proton from the acid, okay, it's accepting a proton from the acid, it is a base in this case. So water we think of as neutral, but actually depending on the situation I put it in, it can either be an acid or it can be a base. And in this case it's a base because it's accepting a proton, so it turns into the hydronium ion. And the hydronium ion is an acid particle. Now what you can see here is we have two acid-base pairs. There is a pair that are similar but different by only the hydrogen and the positive charge, and then that is this HCO3, okay, and the CO3 2-. And then we have another pair where the acid is the H3O+ and H2O. That's an acid-base pair. That is an acid, and so that is an acid-base pair as well. So think about it this way. If we had hydronium ion and carbonate ions, actually the hydronium ion would give the proton to the carbonate ion and the reaction would go backwards and make the weak acid in the base. And that's why this reaction is at equilibrium. Okay, if we look at the next reaction, if we study it carefully, we see the two reactants are ammonia, NH3, and water, H2O. One of them is acting as a base and one of them is acting as the acid. So we look on the right-hand side and we see, is there a species on the right-hand side that pairs up with the ammonia, the NH3? Yeah, there is. There's an NH4+. That's just ammonia with one extra proton. So what has happened to ammonia here on the left-hand side, it has, as it went across, as it reacted, it accepted a proton from the water molecule. That's how it became the NH4+. And the water molecule must have donated a proton, okay? So it must be an acid. When the water donated its proton, it lost a hydrogen and it lost a positive charge and it became an OH-. Now you can see here again, we have acid-base pairs. Pairs of conjugate acids and conjugate bases. They are species that are different, molecules, ions that are different by just one hydrogen and one positive charge. And now obviously the acid for the ammonia pair is NH4+, and the base is NH3+. And the acid for the water pair, in this case, water is acting as an acid, and the hydroxide ion is the base. Now, these are conjugate acid-base pairs. One other thing we can notice here is sometimes there are species that, depending on their situation, can be a base or can be an acid. So water can be a base when it's with a weak acid, or it can be an acid when it's with a weak base. They're called amphoteric or amphiprotic. Okay, let's have a look at the next idea here. Okay, so let's look at some specific types of acids and bases. What is a strong acid? Well, a strong acid is, obviously it's an acid, so it's going to donate a proton to water to produce hydronium ions. But because it's strong, the word strong indicates that when it reacts with water, every single acid particle reacts with as many, correct number of water particles as it should do. It fully dissociates. So we use this terminology, fully dissociates, to say that it fully reacts with the water. It's not at equilibrium. It has just an arrow that directs to the right. And in this case, you can see hydrochloric acid is the acid. It's donating its proton to water, and it's becoming a base. A conjugate base. It's not actually a base. So the particular thing about strong acids is because they are strong acids, because they can only move in the forward direction, the chloride ion cannot actually go backwards and make the acid again. And that makes this actual chloride ion neutral. And in fact, any negative ion that is produced from a strong acid is neutral. If you put it in water, it will produce a neutral solution. It's not acidic and it's not basic. So chlorides, nitrates, sulfates, bromides, they are all neutral ions. Anyway, strong acid fully dissociates in water. What that means is that the concentration of hydronium ions, the H3O pluses, is exactly the same as the concentration of the hydrochloric acid we started with. If we had 2 moles of hydrochloric acid, we would make 2 moles of hydronium ions. That's really important when we carry out our calculations to work out pHs. So here are the common strong acids that we need to memorize and remember their names. There are 4 of them here: hydrochloric acid, HCl, hydrobromic acid, HBr, nitric acid, HNO3, and sulfuric acid. And notice here that they all react with water to produce hydronium ions. Okay, the only difference is they're producing these negative ions, okay? And they're different because they were different acids. Now remember, I said each of these negative ions is actually, even though it's called a conjugate base, its properties are that it's neutral. One thing to notice about sulfuric acid, in case someone asks you, there is a ratio of 1 sulfuric acid reacts with 2 waters, right? It undergoes 2 protonations. So it produces the sulfate ion. But each one of these ions are actually neutral, okay? But remember, the most important things about strong acids, they fully dissociate in water and they produce hydronium ions. Strong bases. Okay, strong bases are different. We kind of deal with them a bit different here. Now, they do fully dissociate in water, but they don't dissociate in the same way that strong acids do. So here, this is a polar water molecule. We'll remember this from the other work we've done in chemistry this year. The red circle represents an oxygen atom, with the white circles representing hydrogen atoms. Now, because it's polar, one side of it is slightly negative, delta minus, and one side is slightly positive, delta positive. Now, when we take this molecule, okay, and we put our strong base in water, it actually breaks apart into ions. It doesn't react with water in the same way that the strong acid did. What it does is it does dissociate. Sodium hydroxide is an ionic lattice. Looks like this, right? Sodiums, hydroxides in an alternating 3D arrangement of ions. Okay, so they're in this regular 3D lattice. Now what happens is the actual water particles come up, and the positive hydrogen side of the water molecules is actually attracted to the negative OH, and they go there and they make strong attractions with this hydroxide ions, attractions that are just as strong as the attractions they have within their lattice, and it pulls them away and it dissolves them. So when you see a strong acid, it's not accepting or donating a proton to water, it's just been dissolved, and the hydroxide that was part of the lattice is the negative hydroxide ions in the solution that give it its basic properties. So the types of strong acids we need to know the names are sodium hydroxide. Again, it dissociates. Now, when we're showing the strong acids dissociate in water, we don't go plus water, because remember, they're not actually they're not accepting protons from water. But what we do is we just put the water above the arrow. So the sodium hydroxide is turning into sodium ions and hydroxide ions. And then potassium hydroxide, again, turns into potassium and hydroxide ions. You can actually get lithium hydroxide as well. And the lithium hydroxide would do the same. Sorry, just skipped that. Calcium hydroxide I had on the slide, what it does is it actually, when it breaks apart, because it's calcium OH2, it would break apart into twice as many OH ions. So what about weak acids? Okay, let's compare them to those strong acids we talked about initially. They partially dissociate in water. What do I mean by that? What I mean by that is they are equilibrium. There is an equilibrium reaction happening here, both a forwards and a reverse reaction. And in fact, when this weak acid, which is the ammonium ion, when it reacts with water, it's going to produce ammonia plus hydronium. But the equilibrium is actually so far to the left, so there is so many reactants compared to products. It's like a 1 to 1,000 ratio. So there's hardly any hydronium ions produced. There are hydronium ions. So because we are producing hydronium ions, the ratio of hydroxide and hydronium ions in the solution means that there are more hydronium ions than hydroxide ions. So it is going to be an acid, definitely, right? Because if it was neutral, the OH minus ions and the H3O plus ions would be equal concentrations. But no, we're adding more H3O plus ions. It is going to be an acid. But the amount of H3O plus ions is nowhere near the concentration of the NH4 plus ions for a start, because it partially dissociates. And we use that terminology, partially dissociates, right? So this is the acid, that's the base. They're acid-base, conjugate acid-base pair. Now, there are like a few different weak acids. They'll add some extra ones in. You'll know that they're weak acids because of the properties they might tell you about them, their pH, whether they conduct electricity. Weak acids always have a pH that is less than 1 and 2, maybe 3, 4, 5 pH. They don't conduct electricity well most of the time. I mean, NH4 plus does conduct electricity well because the NH4 plus is an ion in the first place. But things like ethanoic acid, let's have a look at this. See, ethanoic acid reacts with water. Ethanoic acid is neutral, water is neutral, and produces ions. But the concentration of ions on the right-hand side is so low, it won't conduct electricity very well. Because it produces a low concentration of H3O plus, it doesn't have a really low pH. It has a pH lower than 7, but not very low. Methanoic acid, okay, same thing. It's another organic acid. It's going to produce a low concentration of H3O plus, but remember, it's always going to be more H3O plus than OH minus, so its pH is above 7, but it's somewhere in the mid of range between 1 and 7. Ammonium ions. Now, this is different in that it started with an ion and now it's turning into a neutral molecule. So if someone asked me whether it conducted electricity, well, I'd go, yes, it does, because the NH4 ions that were present in the solution conduct electricity. And not many of them have turned into NH3s, maybe 1 in 1,000. So a conjugate acid, remember, a conjugate base of a weak acid is actually a weak base. So even though these are all called weak acids, the bases they make, their conjugate bases, are weak bases. So we could take anything on the right-hand side and call them bases, but they're not strong bases, they react as weak bases as well. Okay, let's have a look at a weak base then. Weak base, weak, partially dissociates, base is going to produce hydroxide ions. Okay, here's the base here. It's going to react with water and produce. Notice that we've got ammonia this time. That was the conjugate base of NH4 plus, NH3. But now it's a base itself, and the NH4 plus is the conjugate acid. And the acid that's produced from this base is a weak base in itself. So these conjugate base acid pairs, okay, are weak acid, weak base pairs as well. Now, carbonate ion. If it acts as a weak base, we're going to have to put it with water. It will partially dissociate. That means we'll have a double arrow. It's going to accept a hydrogen and a proton. So it was 2 minus, it now becomes 1 minus, and we get an extra hydrogen. And as it does this, it produces a hydroxide as well. That's what makes it basic. But remember, the amount of hydroxide it produces is only small. It's like 1 in 1,000. So it is going to have more hydroxide in the solution than it does hydronium ions, H3O plus ions, but they're not going to be as concentrated if it was a strong base. So the pH for this type of weak bases is, it's going to be somewhere around about, maybe between about 9 to 11. Ammonia, same thing, reacts with water, produces the ammonium ion plus OH minus. And the methanamine here, it's going to produce the methammonium ion and the OH. Now, if they asked you about conductivity again, notice the first base that I had here, weak base, carbonate. Of course it's going to conduct well because carbonate is an ion for a start, okay? And not much of it turns into this hydrogen carbonate, even though the hydrogen carbonate is an ion. But if we go to ammonia, NH3, it's a neutral compound. So if it did this dissociation with water, it would only produce a very low concentration of NH4 plus and H3O plus. Or OH minus, sorry. So therefore, it would be a poor conductor of electricity. It wouldn't conduct the electricity very well. It would a little bit, but not very well. And that's the same with the methanamine. Okay, so we can summarize these into a table because the important facts that we need to know about them is strong acids, weak acids, strong bases, weak bases. We need to learn the what's in each of these what each of these groups are, what things are strong strong acids, what are weak acids, what are strong bases, what are weak bases. And then we need to know that when it's strong, it means fully dissociates. And when it's weak, it means partially dissociates. Once we know that, we go, okay, because it's a strong acid, fully dissociates, its pH must be 1 to 2, right? That's if its concentration is 0.1. If its concentration is really low, then it won't actually have that pH. But just a concentration of 0.1 moles per litre, it should have a pH of 1 to 2. But a weak acid, okay, a weak acid is going to have a pH between about 3 to 5 because it partially dissociated and a small amount of it went to the other side. Strong base. Okay, because the strong base completely, remember, we had this ionic solid that had the water molecules come and attract them away and they fully dissociated in water. Now, because they fully dissociated, the amount of OH minus ions is going to be equal to the concentration that the ionic solid was in the first place. So it's going to have a high concentration of ions and it's going to have lots of OH minus. It's going to have a pH of 13 to 14. Weak base, again, because it partially dissociates, it's going to have a pH around about 9 to 11, right? So only so many OH minus ions, more OH minus ions than H2O plus, so pH must be larger than 7, but not enough to give it a 1 to 2 pH. Now remember, we look at how many ions are produced. If something is a strong acid, completely dissociates, produces a high concentration of ions, good conductor of electricity. Weak acid partially dissociates, small concentration of ions, and a poor conductor of electricity, unless, remember, unless the weak acid itself was an ion, then it's going to be a good conductor of electricity. Strong base, good conductor of electricity because it's just an ionic lattice that's dissociated. So we've got lots of ions, conducts electricity well. Weak base, poor conductor of electricity, unless, we started off with an ion. So it's the same caveat as we had for the weak acid. Okay, comparing weak acids and strong acids will often be a question when they ask the exam, will ask you to make a comparison between weak acids and strong acids. So imagine that we have a 1 mole per litre solution of ethanoate and of weak acid, ethanoic acid, and the strong hydrochloric acid. So we've got two solutions, one of ethanoic acid, that's a weak acid, and one of HCl, it's a strong acid. So here's our ethanoic acid, right? So remember, what were the key terms that we knew about this? So there is a double arrow there, so we know that it partially dissociates. Remember again, what's the concentration like of H3O plus? Because it partially dissociated, the concentration of H3O plus is low, right? It's still bigger than the OH concentration, but it's low. What's the concentration of the combined, of all the ions? Well, it's still low because it partially dissociates. So we can say here that ethanoic acid is a weak acid, so it partially dissociates in water. That's explaining what we wrote in our equation. only a very small concentration of ions are produced, so it will have a higher pH, right? Higher, we need to make sure we get this correct. Higher means a larger number. Even though it has a lower concentration of H2O plus, its pH number is going to be higher because a higher pH number means a lower concentration of H2O plus. And it will be a weak conductor of electricity because it actually has this low, small concentration, okay? What about strong acid? Well, strong acid fully dissociates, completely dissociates. It's going to have 1 mole per litre of H2O plus and 1 mole per litre of Cl minus. It will have a pH of 1 because it has a high concentration. It actually doesn't have a pH of 1. If I put that as 0.1 mole per litre, it would have had a pH of 1. This is going to have a pH of 0. But anyway, it's got a really low pH. Because of high concentration of ions, it's going to produce electricity. It's going to conduct electricity really well. Strong conductor of electricity because it can transfer the charge efficiently, right? What about a salt of strong acids? What a salt of a strong acid? Well, strong acid salts. So let's have a look at strong acid salts. Any salt produced from an ion that is a strong acid, and we talked about this before, chlorides, nitrates, sulfates will be neutrals. Okay, so this solution, the sodium chloride solution, if anyone gives me a solution of sodium chloride, I know sodium's mostly just a spectate ion, but the chloride ion, because it derived from a hydrochloric acid, it's going to be neutral. The solution will be neutral. Potassium spectate ion, when we dissolve this solution, this lattice, the sulfate ions will not react with water because they won't go backwards and make the sulfuric acid because the sulfuric acid is so strong. So the ions produced are neutral. They'll have a pH of 7. So if you ever see the ions that would have come from a strong acid, a chloride ion, a sulfate ion, a nitrate ion, or a bromide ion, they're always going to be neutral, pH of 7. Okay, salts of weak acids. So the substance that is an ionic solid that contains a positive ion that is a weak acid. When placed in water, this separates into positive ions. Okay, so these are not salt. These are weak acid salts. So weak acid salts, here's what they look like. So here's a weak acid salt. It's a salt that when we put it in water, it makes a weak acid. Here it is. And it's made this ion too. Now we know that the chloride ion is neutral because it came, it could have come from a strong acid. But this ion here, we should recognize this. This is a weak acid. So the very first thing we do if we have a weak acid salt is we draw its lattice breaking apart into its ions. That's what this is here. This is the same as we had for our strong base, remember. This is a lattice, an ionic lattice of alternating ions. It's breaking apart into these ions. But because the NH4 plus, okay, the NH4 plus, because it is a weak acid, we recognize it's a weak acid, we know that it's going to go on and do another reaction. So it's going to react with water, it's going to partially dissociate, and it's now going to produce this H2O plus and the NH3. So we have two reactions that have happened here. First, we put the ionic lattice into the solution. It broke into ammonia ions and chloride ions. The ammonium ions are weak acids, so when they donate their protons to water, they become hydronium ions and NH3. So this is going to have a pH, right, that's higher than 7 because it's produced these hydronium ions particle. We're going to have a higher concentration of hydronium ions to hydroxide ions. But it's not going to have a pH as high as 1 to 2 because it only partially dissociated. Now, weak acid salts, we have ammonium chloride, a common one, methanamine chloride. We also might have something like sodium fluoride. That's another salt of a weak acid. Not a salt of a weak acid salt. Now, these solutions have high concentration of ions and conduct electricity. So whenever we have a weak acid salt, right, because a salt means it's an ionic lattice that's made up of positive and negative ions. They are always going to be amazing conductors of electricity because we're going to have the spectator ion, like this chloride ion above, and we're going to have this ammonium ion, and only some of the ammonium ions will actually react with the water. So we've got this high concentration of ions. It will always conduct really well. Okay, weak base salts. Okay, so when we put a weak base salt into water, it's an ionic lattice again, sodium ethanoate. Okay, when we put it in water, it breaks apart into the ethanoate ion and the sodium ion. Now, sodium, potassium ions are always neutral. Okay, so we've got these neutral ions, and we know that this ethanoate ion on the right-hand side, because we've learnt our weak acids, right? We learnt what they were. We can see it's the conjugate base of a weak acid. So this is actually going to be a base. So when I put this negative ion and I react it with water, because it's the conjugate base, it's going to react with water and it's going to make the ethanoic acid and the hydroxide ion. Now, because it's doing a partial dissociation, it's got a double arrow here, and it's only producing a small concentration of ethanoic acid and hydroxide ions. So it will produce hydroxide ions, and the concentration of hydroxide ions will be bigger than the concentration of hydronium ions. So it's going to be a base. pH is going to be bigger than 7, but it doesn't produce a large concentration of OH ions because it only partially dissociates. So its pH is going to be between 9 and 11. Other weak acid salts that we might see: sodium ethanoate, sodium carbonate, and sodium fluoride. Okay, these solutions have high concentrations of ions and conduct. Yeah, remember, they were all lattices. Whenever we hear the word salt, it means it's an ionic lattice. It will break apart in water. Okay, so salts are ionic lattices that dissolve in water, like sodium chloride, table salt. But sodium chloride, remember, when we put it in water, it breaks into sodium ions and chloride ions. Sodium ions are neutral, chloride ions are neutral because they're conjugate bases of a strong acid. Okay, weak base salts. Exercise. Describe the pH and conductivity of the salt sodium carbonate. Include all relevant equations. Okay, so they've told us it's a salt, and remember, we know a salt fully dissociates in water. Here we go. So, here's our salt dissociating in water. It's producing, remember, because it's a lattice breaking in water, I've been very careful here. I've actually put, I know it's a solid, so I put the brackets with the S in to show its phase. And I know that it's dissolved in water, so it's aqueous. So the others, you can leave those out. You don't have to have those there, but they do give more clarity to this equation. So I've got 2 sodium chloride plus carbonates. Cool. So dissolved in water. Now I'm looking at this carbonate and I know, okay, is carbonate going to donate a proton or something? Of course not, because it's got no hydrogens. But we know that it might accept a proton and become hydrogen carbonate. And we've remembered that carbonates are actually weak bases. So because it's a weak base, it partially dissociates. I know that I'm going to put a double arrow here. So I've got my carbonate reacting with water. Water is donating a proton to the carbonate. It's becoming hydrogen carbonate. And we're making some hydroxide ions. Now, because we made some hydroxide ions, okay, what's happened here is this is going to be a base. Because it partially dissociated, this weak base, it's not going to be a strong base with a pH of 1 to 2, but it's going to be a weak base. We're going to expect a pH between 1 to 2, I mean 12 to 14. It's going to be a pH between 9 and 11. Okay, now, because in the first instance, the lattice fully dissociated in water, it's going to conduct electricity really well. Okay, important to know. And remember, because it partially dissociates, concentration is low, but still higher than H2O plus concentration. So the pH is about 10 to 7. Okay, comparing solutions. This is a question that they might ask us. 3 solutions, X, Y, and Z, have lost their labels. The labels were known to be hydrochloric acid, potassium nitrate, and ethanoic acid. The pH of each solution was tested and recorded below. So here's the pH. So each one of those things, hydrochloric acid, potassium nitrate, and ethanoic acid is one of those solutions. How do we work out which is which? Well, if you remembered, HCl is a strong acid because it has a pH of 0.1, sorry, a concentration of 0.1, and will have the same concentration of H2O plus because it fully dissociates. So this HCl is going to have a pH of 1. Okay, now I'm thinking about this before I write it down. The next thing, potassium nitrate. Well, I know potassium is always a spectator ion, so it's going to be neutral. What about a nitrate? Where did that come from? Well, it's a conjugate base of a strong acid, so it's neutral as well. Do I have a neutral pH? I do. So KNO3 is actually Z. Ethanoic acid. Well, I remember it's a weak acid and there's a 3.4, so I'm pretty happy with that. So Y must be HCl, fully dissociates, high concentration of H2O plus. Z, potassium nitrate, because of neutral potassium and nitrate ions. And X is the weak acid that partially dissociates. Therefore, pH in the acid range, but not as small as a strong acid. There we go. Okay, amphoteric, amphiprotic substances. So, like we talked about this before. So, hydrogen carbonate is an amphiprotic substance. It can donate a proton or it can accept a proton. So, what do I mean by this? So, here's hydrogen carbonate here. I can add it to hydronium ion, and when the hydronium ion is with it, the hydronium ion will donate another proton because the hydronium ion is quintessentially, it's the acid. It's like the definition of an acid, right? So it donates its proton to it and it becomes dihydrogen carbonate plus water. But what if I put that hydrogen carbonate with a base? Yeah, with a hydroxide ion, the quintessential hydroxide ion. So if I put it with that, then what we're going to get is the OH is going to accept or suck the proton off the hydrogen carbonate and it's going to make a carbonate ion. So in this case, in the top case, the hydrogen carbonate acted as an acid, as a base, and in the bottom case, it's acting as an acid. Therefore, it can be either an acid or a base depending on its situation. It's said to be amphiprotic. And we can just call it amphoteric. Amphiprotic means it can either donate or accept a proton. Amphoteric means it can react with an acid or a base. There might not be a proton. Okay, so here's a question that brings all of this together. Hydrogen iodide is a strong acid, where hydrogen fluoride acid is weak. Write equations to solve these reactions. So what I want you to do is look at these two equations. I want you to write the answers, but pause the video first, write the answers, and then start the video again. Okay, hydrogen iodide is said to be a strong acid, therefore fully dissociates in water. It's going to donate a proton to water. It will produce iodide ions and hydronium ions. Now, hydrogen fluoride will produce similar products, but because it is said to be a weak acid, remember, it partially dissociates. So we draw an equilibrium arrow and it will produce a fluoride ion and a hydronium ion. Okay, for part B here, it says solutions of both hydrogen iodide and hydrogen fluoride are made up of to the same concentration. Explain how the pH and electroconductivity of the two solutions would differ. Okay, again, have a go at answering this question and pause the video and restart it once you've done it. Okay, so hydrogen iodide, we can see at the top, it fully dissociates in water. So the first thing that we're going to say is, here we go. I put this in the wrong order. Hydrogen iodide fully dissociates in water. It produces high concentration of hydronium ions and chloride ions. Okay? It will have a pH of 1. Well, it will have a high pH because it produces a high concentration of H2O plus ions. It will also be a strong conductor of electricity because it has a high concentration of ions in total. Hydrogen fluoride is a weak acid because it partially dissociates. It has the equilibrium arrow. only a very small concentration of fluoride ions and hydronium ions are produced, so it will have a pH higher than the hydrogen iodide. Okay, it will still be above 7 because it has more hydronium ions than it does hydroxide ions, but it won't be nearly as high as a hydrogen iodide. It will also be a weak conductor of electricity because if we look at it right here, we can see there's only a small concentration of ions produced. Conducts electricity poorly. That's the example. I hope this video helps you with getting your head around acids and bases. Look out for the next video.